The promise of artificial intelligence often conjures images of fully autonomous systems, but the journey from abstract concept to functional code is a rigorous engineering challenge. Before any AI can be considered truly harnessed for real-world tasks, a foundational understanding of its core principles and practical implementation is paramount. This video demystifies those initial stages, focusing on translating theoretical AI concepts into tangible, implementable code. We will cover essential principles of model selection, data preparation, and the foundational architectural considerations necessary before an AI can be deployed. The emphasis will be on building a robust and well-understood starting point, ensuring that the AI's capabilities are not just powerful, but also predictable and reliable. The initial hurdle in developing any AI system is selecting the appropriate model. This decision is not arbitrary. It hinges on the specific problem the AI is intended to solve. For instance, classifying images demands a different architectural approach than predicting time series data or generating natural language. A common mistake is to opt for overly complex models when a simpler one would suffice, leading to inefficient resource usage and potential overfitting. Overfitting occurs when a model learns the training data too well, including its noise and idiosyncrasies, making it perform poorly on unseen data. Consider the task of image recognition. Convolutional Neural Networks, or GNNs, have become the de facto standard. Their architecture, inspired by the human visual cortex, uses convolutional layers to automatically and adaptively learn spatial hierarchies of features from images. However, choosing the right GNN architecture, whether it's a ResNet, VGG, or inception model, depends on the dataset's size and complexity, as well as computational constraints. A deeper network might offer higher accuracy but requires more data and processing power, a trade-off that must be carefully managed. Data preparation is another critical, often underestimated phase. Raw data is rarely in a format suitable for direct input into AI models. It requires cleaning, transformation, and normalization. Cleaning involves handling missing values, correcting errors, and removing duplicates. For numerical data, normalization or standardization is crucial to bring features onto a similar scale, preventing features with larger values from dominating the learning process. For example, if one feature ranges from 0 to 1 and another from 0 to 1000, the latter would disproportionately influence distance-based algorithms. Text data presents unique challenges. Before it can be processed by most AI models, it must be tokenized, broken down into individual words or subword units. This is typically followed by converting tokens into numerical representations, such as one-hot encoding or, more commonly, word embeddings like word2vec or glove. These embeddings capture semantic relationships between words, allowing models to understand context and meaning. The quality and relevance of these embeddings significantly impact the performance of natural language processing tasks. Feature engineering is the art and science of transforming raw data into features that better represent the underlying problem to the predictive models, resulting in improved accuracy on unseen data. This can involve creating new features by combining existing ones or extracting domain-specific information. For example, in a financial forecasting model, instead of just using raw stock prices, one might engineer features like moving averages, volatility indicators, or the spread between bid and ask prices. Architectural considerations extend beyond the specific model type to the overall system design. How will the model be integrated into an existing application or workflow? What are the latency requirements? What are the computational resources available for training and inference? These questions dictate choices about model complexity, the use of specialized hardware like GPUs or TPUs, and the deployment strategy. A model that performs exceptionally well in a research environment might be entirely impractical for a real-time, on-device application due to its computational demands. The choice between different types of neural network architectures is often a crucial decision point. For sequential data, recurrent neural networks and their more advanced variants like long short-term memory or gated recurrent units are employed. These models have internal memory mechanisms that allow them to process sequences of data, making them suitable for tasks like natural language understanding, speech recognition, and time series analysis. However, standard RNNs suffer from the vanishing gradient problem, where gradients become exponentially smaller as they are back-propagated through time, making it difficult for the network to learn long-term dependencies. LSTMs and GRUs were developed to mitigate this issue through sophisticated gating mechanisms that control the flow of information, enabling them to retain relevant context over much longer sequences. For tasks requiring understanding relationships between different parts of data without a specific sequential order, graph neural networks are increasingly relevant. GNNs operate on graph-structured data, such as social networks, molecular structures, or knowledge graphs. They propagate information between nodes in the graph, learning representations that capture both node features and the graph's topology. The scale of data also dictates architectural choices. Training massive deep learning models, especially those with billions of parameters, requires distributed training strategies. This involves splitting the model and/or data across multiple processing units, often across multiple machines. Techniques like data parallelism, where the same model is replicated on different devices with different batches of data, and model parallelism, where different parts of a single model are placed on different devices, are essential for tackling large-scale AI development. Furthermore, the ethical implications and potential biases within the data and the model must be considered from the outset. Building AI systems that are fair, transparent, and accountable requires careful attention to data collection practices, model evaluation, and the potential for disparate impact on different demographic groups. Addressing bias is not merely a technical problem but a fundamental requirement for responsible AI development. Before code is written, a clear understanding of the problem domain, the available data, and the desired outcome is essential. This conceptual phase involves defining metrics for success, establishing baseline performance, and understanding the constraints and limitations of the potential AI solution. Without this clarity, development efforts can quickly become unfocused and inefficient. Translating these conceptual requirements into code involves selecting appropriate libraries and frameworks. TensorFlow and PyTorch are currently the dominant deep learning frameworks, each offering a rich set of tools for building, training, and deploying neural networks. The choice between them often comes down to developer preference, existing infrastructure, and the specific features required for a project. The actual coding process involves defining the model architecture, setting up the data loading and preprocessing pipelines, defining the loss function and optimizer, and implementing the training loop. This iterative process requires careful debugging and performance monitoring to ensure the model is learning effectively and efficiently. Ultimately, harnessing AI is an iterative process of conceptualization, data preparation, architectural design, and rigorous coding, all underpinned by a deep understanding of the problem domain and a commitment to responsible development practices. The journey from a theoretical idea to a functional AI system is complex, but by focusing on these foundational elements, we can build robust and reliable intelligence systems for the future.